Hello, good morning, everybody. We are going to start the lectures on the basic concepts of distribution theory in this video. We shall have very basic concepts like random variables, distribution function, probability mass function, probability density function, etc. in this video. Now, we have first the concept of a discrete random variable. If a random variable takes at most a countable number of values, it is called a discrete random variable. Or in other words, a real valued function. It is a real valued function. Discrete random variable is a real valued function defined on a discrete sample space. Okay. You might have heard a lot of examples of discrete random variables, and I'm not going to discuss any example here, but we will have to discuss many examples in course. Probability mass function, or PMF, is associated with a discrete random variable. Suppose x is a discrete random variable taking at most a countably infinite number of values, say x1, x2, etc., with each possible outcome associated with the random variable, that is x equal to xi, we associate a number, a real number pi, which is also denoted by p of xi, which is equal to probability that x takes the value xi. This function p is called probability mass function of the random variable, and the value pi or p of xi is the probability of xi, or probability that x takes the value xi. Okay, and these numbers p of xi, actually p of xi is a real number, and this real number p of xi must satisfy the following conditions. One is p of xi greater than or equal to 0, that is, this number, this real number is always a non-negative real number for all I, and second, their sum is equal to 1. And this function, as we have already argued, p is called the probability mass function of the random variable x. And the probability mass function can be explained in terms of an array of real numbers xi's, that is the values assumed by the random variable and corresponding probabilities. Such an array is called the probability distribution of x. You can write down this array in the form of a table with the x values and probability values. You can have a simple example of tossing of a coin whose sample space is f is equal to set ht, where h stands for the occurrence of head, t stands for the occurrence of tail. And you can define a random variable x as x of h equal to 1, that is x equal to 1 if head occurs, and x of t equal to 0, that is x takes the value 0 if tail occurs. And you can find the probability mass function by p of x equal to 1 equal to 1 by 2, p of x equal to 0 is equal to 1 by 2, etc. Because when a coin is tossed, both the faces head and tail are equally likely to occur if the coin is fair. So there are two real numbers, p of x equal to 1, that is p of 1 equal to 1 by 2, and p of 0 equal to 1 by 2. Now this is the probability mass function. Okay. And distribution function is a very important concept to be discussed when we speak of random variables. With every random variable, whether it is discrete or continuous, we can associate a function called a cumulative distribution function, CDF, or simply distribution function, DF. It is called cumulative distribution function because you can see later that this is a probability which is summed up or added up. And the definition is straightforward. The cumulative distribution function or CDF of a random variable x, it is denoted by f of x. Capital X in the suffix stands for the random variable capital X. And you need not write the suffix capital X if you are dealing with only one random variable, but you have to add the suffix when you discuss more than one random variable, say for example capital X, capital Y, capital Z, etc. Okay, this f of x equal to probability that x takes the value less than or equal to small x, that is the probability up to and including small x. And you note that this definition is for all x, okay, not only for the values assumed by the random variable x, but for all real numbers. In the case of discrete random variable capital X defined above, you can see that fx is equal to summation of all probabilities up to and including x. Summation because you are dealing with a discrete random variable. For all probabilities up to and including x. Okay. And you take this example of tossing 3 coins and you define the random variable x denoting the number of heads when these 3 coins are tossed simultaneously. And you know the sample space is very clear, and you can see that the x takes the value 0, 1, 2, 3, 0 when TTT occur, 1 when TTH or THT or HTT occur, because in these 3 cases you are having only one head, so x takes the value 1, and so on. And you can compute that these probabilities are 1 by 8, 3 by 8, 3 by 8 and 1 by 8, because in the first case there is only one case out of 8, and in the second case there are 3 cases out of 8, and so on. So this distribution function can be computed like this. F of x equal to probability that x up to small x. Okay, and this is defined for various ranges from minus infinity to infinity. Now you see that from minus infinity to 0, but 0 is not included, there is no probability, so f of x equal to 0. And in the second range, 0 to 1, 0 inclusive and 1 exclusive, probability is 1 by 8, because in this case only probability that x equal to 0 is to be included. In the third range, that is 1 to 2, 1 inclusive and 2 exclusive, you have to include 0 as well as 1. So you have to add probability at x equal to 0 and probability that x equal to 1. So you have to add 1 by 8 and 3 by 8, so that it is 4 by 8, or f of x equal to 1 by 2. And similarly in the range 2 to 3, 2 inclusive, 3 exclusive, whatever be the value you are considering for x in this range, you have to add the probabilities 1 by 8, 3 by 8 and 3 by 8, so that it is equal to 7 by 8 total probability up to and including x. And finally, when x greater than or equal to 3, you have to include the values assumed by the random variable 0, 1, 2 and 3. So you have to add 1 by 8 plus 3 by 8 plus 5 by 8 plus 1 by 8, which is equal to 1. So in this way you can compute the distribution function of the random variable x. Okay, and here a very important point which I have just argued that f of x is defined for all x minus infinity to infinity, the real line, and not for those values in the set of values assumed by the random variables 0, 1, 2 and 3 only. Okay, so this f of x is defined for all real numbers, and you can see that in between these numbers 0 and 1, 1 and 2, 1 and 2, 2 and 3, etc., f of x is constant. For example, you can see that f of x in this range 1 to 2, 1 to 2, in this range, what happens in this range? Whatever be the value of x in this range, f of x is 1 by 2. So it is a constant in the entire range of 1 to 2. And similarly in the entire range of 2 to 3, probability is constant. Okay, and in the range 3 to the highest value, that is my plus infinity, it is same. Okay, and you see that there is a jump from 0 up to 0, there is a jump. For example, if you have a graph of this function, I will show the graph here. Okay, you can see that in this graph there is a jump at 0. Up to 0, f of x is 0, but at 0 there is a jump to 1 by 8, and it continues up to 1, but at 1 there is another jump, and so on. So this is called a jump function because there are jumps at various points, and this function is in particular called a step function because the graph is in the shape of a set of steps. One step here, then at 0 it has a jump, then a step up to this x equal to 1, and at x equal to 1 there is a jump, then it forms a step, again a step, etc. So this function is in particular called a step function. Okay, and you can see that the function f of x equal to 0 for all x less than 0, because x cannot be negative, and f of x equal to 1 for all x greater than or equal to 3, because x is certain to be less than or equal to such a value. Okay, so up to the first value of the random variable, the least value of the random variable, f of x takes the value 0, and at the value, the last value x equal to 3, there is a jump to 1, and that one will be continued up to infinity. That is why such a function has the shape up to 0, 0, then jump up to 1, 1 by 8, and so on. Okay, these are the concepts of the distribution function, and you can see some very important properties are there for the distribution function, and it is mentioned in the form of a theorem here. You can see that the function f of x is a CDF. It is the statement of the theorem. The function f of x is a CDF if and only if the following conditions are true. That means if these conditions, condition 1, 2 and 3 are true, the function is a distribution function, and any distribution function will satisfy these three conditions. That is why these conditions are called if and only if condition, or necessary and sufficient condition. And you see, the first condition is very obvious, because when x tends to minus infinity, that is when x goes to the left end of the real line f of x equal to 0, and x tends to infinity, f of x is equal to 1. First condition is very obvious, and second condition is also obvious because f of x is a cumulative probability CDF. So you are adding probabilities, not subtracting probabilities. Therefore, you cannot have increased value of f of x when decreased value of f of x when x increases, because it is a cumulative probability. Then third condition is also obvious, that f of x is right continuous. That is, for every number x naught, when x becomes x naught from the right, then the limit of f of x is equal to f of x naught. And this concept is very clear from the figure. You can see that there is a dot at 0, there is a dot at 1, there is a dot at 2, there is a dot at 3 on the vertical axis. And because of the jump nature, it is right continuous. Okay. And we have a technique of computing the probability at any point. Computing the probability at any point of the real line. And that is P of xj. You take xj is any arbitrary value. Then P of xj, by definition, it is probability that x takes the value xj. And it is from the figure, it is very clear that, from this figure, it is very clear that for any value of xj, the probability at x equal to xj is nothing but f of xj minus f of xj minus 1. xj minus 1 is the value just below xj in the support of the random variable. Okay. And the proof is very direct. I have given the proof. Now, for example, x1, x2, etc. are the values, real numbers. Then f of xj is equal to probability that x less than or equal to xj. And you know, this is equal to you are summing up to j. Okay. Then if you take f x j minus 1, that is a probability up to x j minus 1. Okay. And you subtract this quantity from this, so that you will get f of xj minus f of xj minus 1, that is equal to probability of xj, because this probability of xj is the quantity that this right hand side minus this right hand side. Okay. And you can see from this result that once you are given with a distribution function of a discrete random variable, you can compute its probability. Okay. And using this result, you can easily convince that the probability at x equal to 1, probability that x equal to 1 is equal to 1 by 2 minus 1 by 8. Similarly, probability that x equal to 2 is equal to probability at x equal to 2, that is 7 by 8 minus the next least value, that is equal to 1 by 2, and this difference is the probability. Okay. Now all these things you can compute from the formula probability at x equal to xj, that is equal to f of xj minus f of xj minus 1. Okay. Now these are the ideas of discrete random variables, and next video In next video, we will discuss continuous random variables and how the distribution function can be computed for a continuous random variable. Okay, thank you.